Well, welcome to a YouTube channel video about the hybrid layer. I'm Dr. David Alleman. I've been practicing dentistry for 44 years and teaching an advanced approach to adhesive dentistry for 27 years. And these 27 years have been very rewarding because my dentistry has lasted for that long and we don't have to retreat teeth. What is the foundation of this success and longevity of these advanced approaches to adhesive dentistry? The answer is the hybrid layer. Other aspects of restorative dentistry are important. What materials you use, how is the occlusion, how are the caries, and how are cracks dealt with. We teach all of those as part of the overall solution to the problems of restorative dentistry. But after you have a caries removal endpoint developed, and after you've removed dentinal cracks in the surrounding areas around the pulp, then you have the ability to recreate a tooth mimicking restoration that is as strong as a natural tooth. How is that done? That is done by connecting the materials that you're using to the tooth on a molecular level. So what are the molecules that make this molecular connection? Well, the molecules are methacrylate molecules. Remember, in organic chemistry, a methacrylate is something that has two bonds or a double bond in its carbon chain, and that double bond can be attacked by a free radical and makes that molecule now its own free radical that can do the same thing to another methacrylate molecule. Bonding system that's considered gold standard. The smallest molecule, methacrylate molecule that participates in the chain reaction is called HEMA. And it's a very water-soluble molecule, and it's what contact lenses are made out of. Contact lenses are not liquid, they're plastic, but they're soft, but they also mix well with water. So soft contacts are made out of HEMA. Well, those molecules get into the priming of the water that's associated with the dentin after a mild etching procedure, which is called conditioning, or a more aggressive etching conditioning with phosphoric acid. Each bonding system has its way to deal with the conditioning of the smear layer. But these HEMA molecules are the first ones to integrate into the water, which is 20% of dentin. And then larger molecules come into play. And the larger molecules are usually what are referred to as the proprietary molecules of a dental bonding system. And they each have different names. The most important names that we teach in the 6 lessons approach are 10 MDP and 12 MDPB. These are the molecules that have the ability to swim in the water better than larger molecules like GPDM and TEGMA and other molecules that are in bonding systems. But in the hybrid layer, the connection of the tooth that gets partially demineralized and the tubules that have a lot of water in, now we have this priming of these molecules unpolymerized that go into this partially demineralized dentin. And so as they're there, before polymerization, they're still very soft, and we have water that's coming up the tubules. And so that's called transudation. And so if you etch and then spend too much time doing something else and allow a lot of water to come up, then there's spaces between the molecules that are going to be polymerized and this partially demineralized dentin that's going to be integrated into the hybrid layer. But if you have a conditioning step that does not remove hydroxyapatite, in other words, all of the peritubular dentin is in place, and there's a smear plug of chopped up dentin that is in the orifice of every one of the tubules, all of a sudden, there's no pulpal fluid coming up to dilute the placement of these monomers, HEMA, 10-MDP, MDPB, or GPDM. And so that priming step now keeps a close proximity to the hydroxyapatite that's encapsulating the collagen fibers. And so when this adhesive layer now is polymerized, then the reaction goes from the adhesive layer into the primed molecules that are in the partially demineralized dentin, and that becomes integrated micromechanically But in the case of the 10-MDP and the MDPB molecules, actually ionically connected to the hydroxyapatite. So it's a chemical bond with the self-etching, mildly acidic priming systems that are in the self-etching system. That means that there is a connection at these molecules to the molecules of collagen and the molecules of hydroxyapatite. The molecules of hydroxyapatite are, of course, inorganic crystals, and the molecules of the collagen are organic polymers, the collagen proteins. But there is one connection that, once it's made, makes these self-etching systems even stronger. And that is, in our logo on our hat, we have a fourth layer here. And this fourth layer underneath the hydroxyapatite, partially demineralized hybrid layer, which is classically referred to as the hybrid layer, which is 0.5 to 1 micron in thickness. The outer layers of the demineralized hybrid layer in most systems that use an acid etch will have collagen that's completely demineralized or just a little bit of mineralization. And those outer layers of 2 to 3 or even 4 microns really don't give anything to the bond strength. It's only the connection at that last micron that counts. But in the self-etching systems, a phenomena was discovered in 2009 that actually was an infiltration of these very hydrophilic molecules like HEMA and like 10-MDP, able to snake their ways into sound dentin to a thickness of 1.5 microns, even 2 microns. And these areas that are in not demineralized dentin are very, very slightly demineralized dentin from the 10-MDP action. They are now making what's called a acid-base resistance zone. And that is a non-dissolvable area of dentin that has been infiltrated without demineralization. And now the polymerization reaction in that 1 micron or 1.5 microns makes this area even stronger than dentin when it's exposed to an acid or even a basic attack, which would normally dissolve the hydroxyapatite or dissolve the collagen. These acid bases attacks can't dissolve that dentin. So that's why this acid base resistance zone was referred to as superdentin by Tagami when he first introduced it at the International Association for Dental Research in Miami Beach in 2009. I had the opportunity to be at that lecture. Simone Della Peri was sitting right next to me when Tagami says it's the acid-base resistance zone, but we are going to call it a superdentin. That was a big joke. And Tagami knew that he was making a joke on the word super because in 2009, super was an 80s word that we don't use anymore, but he nicknamed it superdentin, and it's been visualized many times since that time. But if you understand that these bonding systems you're using have different approaches, from a Total-etch to a low acidic self-etch system, these are very different ways to approach the conditioning of the tooth, which is how do you deal with the smear layer. If you don't condition the smear layer, you're going to get bond strengths of about 6 megapascals. So smear layer conditioning, the breakthrough in the late 70s was acid etching by Fusiyama. He got that idea from acid etching from Michael Bonacore in the mid 50s. But in reality, the best conditioning is actually abrasion, which thins or even removes the smear layer and the intertubular dentin while compacting a smear plug in the orifices of the tubules. And you get the best of both worlds there. You get a reduction of the dilution of pulpal fluid into the priming solution, and particularly in boxes where you have parallel tubules that are being prepared and the exposure of massive amounts of hydroxyapatite, which is the peritubular dentin. If you do a total etch in those boxes, you're going to have problems. The same thing in near a pulp horn. If you're near a pulp horn and you use total etch near a pulp horn, now you're exposing every heartbeat massive amounts of pulpal fluid, and you will have a gap formed before you have the ability to adhesively seal that area close to the pulpworm if you use a total etch approach. Whereas a self-etch approach with air abrasion compacts any smear layer and makes that as a indirect pulp cap and stops the transudation of fluid. You get a better, more predictable bond strength. So the advantages in the bottom of a deep box and close to a pulpal horn of the self-etching systems, in my view, are very, very large. But of course, it all depends on your understanding of how a hybrid layer is formed. It's the relationship of the molecules to the natural tooth structure that has been not demineralized very much or demineralized a lot, and how that interaction of the molecules when they polymerize happens. The rate of polymerization of a light-cured system, for example, even though they're in a moist, flexible collagen world, they can become stiff enough to make the first layer of a gradation of what's called modulus of elasticity. And so that leads to a concept that's called the elastic wall concept, which has validity, been proven many times by Bart van Meerbeek, who first introduced that in 1993. But this elastic wall concept will only work to a certain degree to relieve stress to the developing hybrid layer. The way that we innovated was a separation or allowing of the maturation to happen without any layers thicker than 1.5 millimeters for the first 5 to 30 minutes in a restoration. And so that idea of protecting the development of the hybrid layer by a decoupling or a separation of polymerization stresses that could negatively affect the hybrid layer, that decoupling or separation is the real key to understanding how to make a long-term successful restoration. The University of Leuven, Belgium, Catholic University of Leuven, Belgium, they've been teaching these preparations that have no retention form, no resistance form, basically flat preparations to increase the bondability of the hybrid layer, because a flat preparation decreases C-factor stresses. The indirect restorations that are done in a biomimetic approach are usually onlays or overlays. An indirect inlay can be done, but usually that would be a restoration that would be best served with a stress-reduced direct composite technique pioneered by Simone Della Peri and myself. Anyway, the hybrid layer, when you start seeing the molecules interacting with the surface, which is pulpal fluid, mostly water, also proteins in there, and the pulpal fluid now is being either contained or expressed into your priming field by having the tubule either plugged with a smear plug or having free flow. And now you're depending on the polymerization and the cross-linking to give a stiffness to your hybrid layer rather than the remaining dentin itself, which in an ideal situation is infiltrated below the actual partially demineralized hybrid layer. And that's the layer that we call the acid-base resistance zone, or a superdentin. Anyway, that's a little introduction to the hybrid layer. If you're interested in learning more, you can go to the link below and find out more about how you can be trained. Till next time, get bonded, stay bonded.